Okay, in case you were not aware of this yet, physics is math-based. If that makes you want to get up and leave the room, too late. This is basically an applied math course. And the hard part, I had a young lady many, many years ago, the first year that they offered the honors diploma, and I had actually, okay, this is the biggest physics class I've had since then. Because I had 27, I had 2 sections of physics, I had 27 and 6, so we had over 30 people taking physics, which was great. Unfortunately, I had a young lady who sat down day one and said, no, you know, look, this is going to be a really good, intense algebra class, and she said, oh, now see, I'm fine with algebra, I just can't do word problems. This is a year of word problems. That's all it is. Because we don't care about the math in isolation, we care about applying the math here, and so it is math-based. It will hone your math skills. Because it is math-based and we are dealing with numeric data, quantitative data, one of the things you have to get really good at, and we're going to work on this all year, is representing mathematical information, numeric information, graphically, and organizing numeric data. So pretty much every lab we do, I think there might be one lab where you don't have to table or graph any data. Every single other one, you will be tabling data, you will be graphing data, you will be comparing graphs, you'll be doing all kinds of fun stuff with data. The other thing, and this is one, I haven't taught physical science for years. If I did, I think I would try to include more of this, because when I've tried to push this into chemistry earlier in the year, I think it really helps with ACT scores. Interpreting graphic information, interpreting graphic representations of data, reading charts and graphs. So we're going to do a little bit of practice with that. When we look at something like that, you need to immediately recognize which one of those has the fastest rate of change. What is the rate of change on a graph? Slope. Yeah. So you should immediately be able to go, oh, that blue line is increasing much more rapidly than the red or purple. If this is a velocity, one of these things is going faster. If this is acceleration, one of these things is accelerating at a greater rate. It also serves as a double check for you. For instance, if you might have done anything ever historically in the last 2 weeks, where you were graphing some numeric data and you had a knowledge of what the slope should be. I don't know if that's ever happened to you in the last 2 weeks in this class. And you knew, for instance, that the slope should be approaching 3.14 or something. I don't know. Then if you got a line that looked like this, you would want to start to question yourself. So that's one of those quick visuals. If you got, and we will talk a little bit about labs later, if you got a line that looked like this, and I think you all know that that's a slope of 1, that's a perfect slope of 1. Up 1 over 1, up 1 over 1. Which is great, and that is a slope of 1 as long as your scales are the same. What if your scales are different? What if this is 1, 2, 3, 4, and this is 5, 10, 15, 20. Then is that actually a slope of 1? Heck no. Sure looks like it if your scales are not the same. So thinking and checking yourself on that kind of graphic stuff is really important in physics. This is something that will happen to you without you even knowing it. You will begin to read equations like books. It's kind of cool. I love algebra. I would do algebra recreationally. I think it's fun. Just manipulating numbers. I mean, it doesn't get you any place new or exciting, but it's sort of satisfying because there's a set of rules and you can just walk through those rules and things are predictable. I like that. I hate to say this is earth-shattering, but I think for me, probably 2 years into teaching physics, I mean, I've always known that math described the world, but there was a moment where I was teaching physics about 2 years in and I went, oh my gosh, no, this really seriously physically describes the motion of this object. Whoa! whoa, that's so cool. I mean, it gives us predictive power. It gives us analytic power. It gives us this amazing toolbox. And so I kind of hope that some of you have at least some little bit of that kind of whoa moment this year. Now, when we're doing physics equations, of which you will do many, there are standard letters that are used again and again and again in physics to represent specific quantities. And once a letter is taken, it cannot be used for something else. So we get into weird situations where like, oh, well, yeah, but they use this for that. So twinkle, twinkle, little star, E is equal to IR. I is current. Why isn't current C? Because C is charge. Ugh. So V is speed, velocity. We'll talk more in chapter 2 about the difference between speed and velocity. That little triangle, that is the Greek letter delta. And I don't think you use this in any of your math classes, do you? In advanced math you did? Okay. So delta is change in. So we talk about change in position a lot in physics. We talk about delta x, delta y. We talk about delta t, which is a time interval. Sigma is another Greek letter, and that's the sum of. So when we get into forces, we'll do sum of forces on the x, sum of forces on the y a lot. T is time. And there are more that are listed in your textbook, but those are some of the ones we use most frequently. So what I want you to do is look at that equation right there and read it to yourself. Delta y equals 3.2 delta t cubed. And we can throw in acceleration, we can throw in all sorts of other things, we can throw in velocity, but you will get good at reading equations. So you're going to get, I'll give you, I don't know, 10 minutes or so to look at those. I think you can probably do it in less time than that. And then we're going to move on together to evaluating expressions, which we'll see if that's as quick as I think it will be.